All right, thank you. And very happy to be here. And I'm glad that you um, put me on the program. I just wish I could have been there in person. Okay, can you see my screen and hear me okay?
Yes.
Okay. So this is co-authored with Manuel Amador and Ricardo Alves Monteiro. So let me just tell you kind of what we're trying to think about in this paper. As you all know, sovereign debt markets have a bunch of frictions in them or inefficiencies. And here's just a list of some of them, probably the major ones. The one that perhaps receives the most attention is that there's very limited state contingency. Most of them are non-contingent. There's some bonds that do have contingencies in them, but usually there's no state contingency. There's an incentive to dilute legacy creditors. I'll talk a lot about that. Their default involves large costs, both directly and through the lengthy renegotiation process. There seems to be evidence that there's self-fulfilling crises, both in Europe as well as in Latin America. We see evidence of this. Currency mismatch. Most of these external bonds are in dollars, although that's starting to change a bit, but that's a major problem. Actually, a lot of what I say relate to domestic currency bonds and inflation risk. So I'm going to talk a lot about the standard kind of default risk, but you could also think about inflation risk as another source of inefficiency with nominal bonds. And then political economy distortions. And I'm not going to talk directly about that today, except as it relates, it's always implicit in this incentive to dilute. There's always a limited commitment problem in there that you can trace back to some kind of political economy distortion as well. Okay, so then with all these frictions, there's an interesting maturity trade-off in this context. So perhaps as is well known, short maturity provides correct incentives, and I'm going to talk about that. It's kind of aligns the lenders and the borrower to minimize the probability of default. Long maturity provides insurance, right? There's safety from rollover risk, and it's a hedge against shocks to endowment or to interest rates. The question we pick up here is floating rate bonds. And I'll show you kind of in the context of the canonical quantitative sovereign debt models that have been popular in the literature, that floating rate bonds provide a happy medium between short maturity and long maturity. So hopefully by the end of the next 25 minutes, you'll understand why that is the case. And how they might be implemented to do this. And I should say at the outset, I mean, there's a literature on kind of when you think about these frictions, about adding clauses, indexing to GDP, indexing to inflation for nominal bonds, buyback clauses. All these things show up in the literature. They don't really show up that heavily in the data. And there's reasons for that. So we're thinking about something that's very simple that we do see occasionally in the data, and we want to understand the economics behind it. Okay, so the standard kind of model: small open economy facing business cycle risk, and we're going to take that as exogenous endowment fluctuations, non-contingent bond with risk-neutral lenders. The contracts are these perpetual youth bonds. They mature with probability lambda. So just like a perpetual youth model, they either mature or they're all identical. And that's an easy way to handle the state variable. We don't have 29-year bonds, 28-year bonds. They're all the same. Either they've matured this period with probability lambda or they just continue on. And they pay a coupon kappa. Okay, and in the standard literature, the kappa is just a fixed coupon. So I'm not going to be heavy on notation or the equations, but I just want to make sure everybody kind of understands the environment. So it's useful just to throw up a couple equations. So this is the value of repayment for the government. So conditional, you come into a period, you decide to repay, as the government, you decide to repay or not. If you decide to repay, then you can issue new bonds, which are B prime, and consume. You can think of this as government expenditure. There's some endowment. You owe the coupon, you owe the maturing bonds, the fraction lambda, and then you roll over the non-maturing bonds and maybe issue new bonds at some price. Okay, Q is the price. This is the value, the continuation value, or the value at the start of a period is the max between the value of repayment and the value of default. All right, and then the price is discounted by some risk-free interest rate, world interest rate. There's the probability that the government will default next period. This is the 1 minus D is the repayment probability. Then they get the coupon, the maturing, and then they continue on. Okay, this is an important object with long-term bonds. Next period, there's some bonds that still exist that have been issued in previous periods. That's going to take a capital gain or loss depending on whether the government's policy in that period is to issue more debt or to pay down their debt. This is what's called dilution in the literature. It's a bit of a misnomer. It's adapted from corporate finance, but it is the idea that future fiscal policy changes the value of the bonds that have been issued in the past, and these legacy bonds are kind of at risk for this. Okay, so that's what I'm going to call dilution. Okay, so the value of short maturity bonds is they have a very clear efficiency property. In fact, they solve a pseudo planning problem. You can think of this planning problem as if the lender and the government get together and write an efficient contract, and the lender gets to choose the fiscal policy. Okay, and so there's this element that these bonds are constrained efficient before we get to rollover risk. I haven't talked about rollover risk yet. So the easiest way to see this is to just think about the government's problem. They have a budget constraint, and then they're out maximizing the value. There's a dual problem to this where we maximize the payoff to the lender subject to the borrower getting some value. And that's more like a Pareto planning problem or a contracting problem. So think about shutting down all sources of risk, except there's a value of default that can be a random draw from some distribution. And so if that value of default is very high, the government's going to default. So the probability that the government defaults next period is the probability they draw a value of default higher than the continuation value, V prime. All right, so we can think about the lender's payoff as they get the payment, Y minus C. They have a continuation value. So 1 minus F is the probability that they're going to survive next period, discounted by R, and then there's some continuation. And then they have to pay the promised value to the government, V. And here I'm just using log utility. Okay, so this is the dual of that problem. And you can write it this way with 1 period bonds, but it looks like a contracting problem. The lenders, it's like they're choosing a path of fiscal policy subject to a promise keeping constraint. So this is the same problem. And this is the first order condition, just rearranged. I set beta R equal to 1, so they don't disagree on discounting. And this is next period's consumption. This is the Euler equation. There's going to be this period's consumption plus an additional term. So there's a slope. Even though the beta R equals 1, there's a slope to consumption. So there's an incentive for the government to save. Here, the lender is choosing this. And the incentive is because at the margin, a higher continuation value raises the probability of repayment, and that factors into the stock of debt. Okay, so this is the efficient contract. The result that we show is that this planning and allocation can be implemented with the 1 period bond. So the interesting question here is, why does the government save in the same way as if the lender were choosing the saving? And the government here has no precautionary reason. We shut down the endowment risk. It's strategic default. The government defaults only if the value of default is higher than the value of repayment. And as I said, this is drawn from a distribution. Why doesn't the government just wait until there's a high value of default? Say there's, some third party is going to bail them out, some debt forgiveness, some reason like that. Why don't they just wait for that? And the key is that they're rolling over their prices. They're rolling over their bond. And every period they have to compensate lenders for the risk of default. So any change in the probability of default immediately gets translated into the prices at which they're rolling over. And so the government internalizes exactly this marginal probability of default, because that is exactly the marginal on the price that they roll over their debt at. Okay, so then we can implement the same allocation with a floating rate bond. And here's how one can do this. Set the coupon on the bond as the implicit yield in a one-period short-term bond, okay? So what is the implicit yield? It's just what I said. There's some interest rate that you have to compensate for the world risk-free interest rate, and then there's some probability of default next period. The way this would be implemented is you auction off a small amount of one-period debt and you index the legacy bonds coupon to this, okay? And we show that this can implement exactly this planning problem. And the idea is the same. Any marginal change in the default probability shows up in the coupon, which is attached to the legacy bonds. And so the government internalizes any change in the probability of default. All right, so they provide exactly the same incentives. Maturity is irrelevant. What really matters is that the government is internalizing any change in the probability of default. The main inefficiency in this model is default. And the government is the only one who can change the probability of default by choosing either more or less debt. The ideal thing is for the government to understand at the margin any change in this friction. And the way to do that is to have this floating rate coupon in this example. Now, there's a couple of caveats to this, and I'll come back to this later. You lose the hedging properties of long-term bonds. Okay, so if endowment risk is floating around or if the world interest rate is floating around, we lose the hedging properties. All right. And then the second thing is there's a source of multiplicity that we call Calvo multiplicity, because Calvo was the one who identified it, is that there's could be many coupons that solve this equation. The higher the coupon, the higher the probability of default next period, and there could be many fixed points to that. And you need a cap on the coupon, okay? All right, now let's add rollover risk. The way we model rollover risk is just called Keyhole. So instead of coming in and deciding whether you default or not and then auctioning bonds, we switch that timing. The government comes into the period, auctions a bunch of new bonds, and then decides based on the outcome of that auction whether they're going to default or not. And this opens the door to a failed auction. They come in with a lot of debt that they have to pay, and no one wants to buy the new bonds. The government really has no option. It's very difficult to repay the maturing bonds without new bonds. And so that zero price can show up as an equilibrium. No one buys the new bonds. They immediately default on the maturing bonds. Here, maturity plays a crucial role, as well as is well known. The less you have maturing, the less vulnerability you have to this kind of rollover risk. So we'd like to have long maturity bonds to avoid this failed auction, so you're not rolling over the entire stock, but we'd like to have incentives. And what we show is that the variable rate coupon on a long-term bond, it could be a perpetuity even, provides the incentives at the margin, but no principal is being rolled over, so it minimizes the rollover risk. Okay, so that's kind of the theory. Then we can take this to the standard quantitative implementation. So take your standard long-term bond model. So Chatterjee Eigenger's AER papers is kind of a well-known version of this. They calibrate to Argentina. We do a couple of different versions of the model. We have one period bonds with and without rollover risk, long-term bonds with and without rollover risk, and then a long-term bond with a floating rate coupon. Okay, so those are our experiments, and we want to just understand the efficiency of these different instruments. Okay, so there's a lot on this slide, so let me just kind of walk through. On the top are different experiments. FR is floating rate, e.g. ST is a standard short-term Eaton-Gersowitz model, basically the same model that I did with Gita Gopinath many years ago, or Christina Ariano did. No rollover risk, one period bond. CK short-term is that same model with Cole Keyhole rollover risk. And then we have long-term bond versions of the Eaton-Gersowitz and the Cole Keyhole. And then we have floating rate where we set the cap on the coupon a little tighter. All right, and I'll talk about that in a bit. Okay, so you can see the standard moments are on here, but let me just highlight in yellow the default rate. So with floating rate bond, we get this is annualized default rate. So this is 0.2% probability per annum that they're going to default. There's very little default in this model. All right, and the debt to GDP, the market value of debt to GDP with different maturities, you can't really compare face value, but the market value is something that's you can compare across maturities. So here, in terms of quarterly GDP, is 0.77. So that's kind of calibrated to what you see in many emerging markets, which is pretty low relative to Europe or the US. But that you see Argentina, Mexico, when they ran into trouble, had fairly low debt to GDP. So we have no defaults in the floating rate. We have no defaults in the Eaton-Gersowitz short-term rate as well. And that's this efficiency property. And that's something that Gita and I discovered many years ago when we were first doing these models, is that with short-term bonds, it's very difficult to get the government to default. We don't get really a lot of defaults with rollover risk in this model, but I highlighted in blue the debt to GDP because in the Cole Keyhole short-term bond model, there's no borrowing. It's so painful to go out and have any vulnerability to this rollover risk. They basically don't borrow. Okay, so they don't have default. They're not exposed to rollover risk, but it's because they don't have access to debt markets, essentially. When we move to long-term bonds, we get a lot of default because of the dilution risk. So here it's close to 7% per annum is the default rate. And this was kind of the contribution of Chatterjee, Eiginger, Hachando, Martinez, et cetera, to show with long-term bond and dilution, you get the government borrowing out and defaulting. And that's inefficient in this model. And the floating rate solved that. Let me just highlight that at the floating rate coupon, we don't get a lot of variation in the floating rate. So the standard deviation of the coupon in this first column in the blue is 0.001 quarterly, right? So it basically doesn't move at all. It does get to 2%. When it needs to be high, it's high. And so the 2% is what it said, okay, what if we put the cap a little bit tighter and put it at 1.5, which was the final column. And there we start getting defaults and we start getting dilution risk. So it is important that you have some scope for the coupon to fluctuate to get the benefits. All right, welfare gains. This is the value of the government at zero debt. On the horizontal axis is the endowment. This is the gain between having a floating rate long-term bond and a short-term debt with rollover risk in consumption equivalent. So 1.01 is that you get 1% more consumption every period to make you indifferent between these two models. So 1% consumption gain is pretty big for macro models. And this is kind of what we get for most of the endowment. Obviously, at very high endowments at zero debt, it's a long way from default. So the welfare gains are smaller, but we get about 1%. With long-term debt, we get also on the order of 1%, a little bit less, but about 1% from moving from long-term bonds with rollover risk. The long-term bonds, at the end of the day, there is no rollover risk because of the maturity, but we do get the dilution, and this is really where the welfare gains here come here. All right. Finally, let me show you two results, both for the short term and the long term, that's useful to think about kind of a pseudo Pareto efficiency. So think about the surplus, the joint surplus of the lender-borrower relationship. So on the vertical axis is the market value of debt at the beginning of the period. This is what the lender's payoff is, the market value on the vertical axis, and the government's payoff is on the horizontal axis. So the line going down is kind of different points on this Pareto frontier. The blue line is short-term debt, okay? The black line is the floating rate debt. So those are almost identical for most of the space, the state space. So if you think about it, this is a parameterized plot. As we move along the and then the point at zero is the default value, right? Zero market value for the lenders, and the government defaults and gets the default value. These differ across models because of the reentry. There's a probability of reentry. So anyway, the takeaway here is that the blue line is short-term debt with no rollover risk. The black line is the floating rate. The red line is the short-term debt with rollover risk. So in the face of rollover risk, the short-term debt is just a terrible instrument, and floating rate avoids these problems and basically mimics a world without rollover risk, but with short-term debt. This is long-term debt. As I said already, long-term bonds basically eliminate rollover risk. So the red and the blue line are on top of each other. It's interesting that this Pareto frontier bends down, so you can be on the wrong side of the Pareto frontier. This is there's a nice paper by Hachando, Martinez, and Sosa Padilla exploring this, that debt forgiveness actually raises both the government's value and the market value of debt with long-term bonds because the legacy lenders are getting diluted. As I said already, with the short-term debt that is with the floating rate debt that's eliminated, and we're only on the downward sloping part of the Pareto frontier, and it clearly dominates this. Okay, so I think I have like three minutes left. Let me just end with a few caveats. So we did have risk in this model, in the quantitative model. We had endowment risk. And the long-term bond provides some hedging properties of this because prices do vary with the endowment risk. And that will show up in the floating rate. But it's kind of dominated by the dilution risk. And it kind of relates back to something that Gita and I talked about in our first paper, and it goes back to Lucas's cost of business cycles. Endowment risk isn't a huge welfare cost compared to these other frictions. What we don't have is risk premia shocks. And we're going to put that in the next version. If you recall Shebnam's presentation yesterday, risk premium shocks, the VIX or the global financial cycle, as Elaine called it, drive a lot of prices, and in particular, they drive sovereign debt prices. That's very clear in the data. And so that would show up in our floating rate coupon. And then there's a question of how that would change our results. So that will be the next version. Stay tuned for that. The second is Calvo multiplicity. We hit that with the cap, but the cap can't be too tight. And obviously with the model on the computer, we're pretty sophisticated about how we can choose a cap that doesn't bind, but eliminates the Calvo multiplicity. In reality, we don't have that kind of sophistication. Finally, let me just mention Italy's experience, which is related because my discussant is from Italy. So Italy had a nice bond, mainly to do with inflation risk. They understood that they had limited commitment to inflation. This is before the euro, but they also had rollover risk. And they introduced this floating rate bond for exactly this purpose. Alesina and Tablima, a very nice paper analyzing this, and they also have a very early model of self-fulfilling rollover problems. Actually, in a volume edited by Draghi and Dornbusch, but they showed that Italy seemed to be manipulating this one-period bond auction. If you looked at the yield curve, the prices started looking out of line with the rest of the yield curve. So that's obviously a problem, is that we're assuming that they can auction off a small amount of one period or one quarter, or whatever you want to call it, bonds, and that there's liquidity in those markets, and there's no manipulation by the government of that market. So that's a caveat that is clearly not in any of these models, but seems to have been relevant to Italy's experience. Okay, I am done.